We are summarizing lecture 3, whereby it was the development of thermodynamics, and it's based on the lecture notes from the Smith notes from page 23 to the end. So basically what we started off was with from slide 6 saying that okay, we can relate length, we can relate length, and we can relate time, and we can relate mass. And in all of this, when we can make new, out of it we can get pressure and all that. And we can get volume. Where is temperature? And so basically the whole thing of this lecture was to get to a point where we can use the thermodynamic postulates, which are accepted and well known, and it's a background fact. It's obviously true, it doesn't need proof. We learned 4 postulates, and from those 4 postulates was shown that okay, we actually know that temperature, it actually comes from thermodynamics. So basically we went on to first, to get there, it was to define the conservation of energy, where E1 equals E2. And by defining the conservation of energy from state 1 and state 2, you can actually incorporate it for potential energy. So you sum up your potential energy, you can sum up your kinetic energy, you can also have internal energy of a substance, and you can add in any other energy in the system like radiation or magnetic energy, and that can all equal to work. But this is incomplete. Therefore, where we went on to more is we used Joule's experiments to just help understand delta U and W, and to get to a point where if you use a piston, that can move up or down, or you use shaft work, you can actually, that is, piston and shaft work is actually all just work. It's work moving in the PV space. So you can either add work by changing the pressure, or you can add work by changing, you can add work by just keeping your piston still, but changing the adding the stirrer on. So basically, you, like in school when you learn the P1 V1 equals P2 V2, it's just with Boyle's law, take into account, okay, the piston, when you have no insulation, like, so you're not using a stirrer and you insulate, it means that you can get work is equal to integral of P dV. But when you fix the volume, you can fix the volume, and you insulate, that means when you insulate Q equals 0, what's happened? Well, you find actually that your, what do you find? You find actually that the temperature increases. So actually if you insulate Q equals 0, but you find that your temperature increases. What that means? It means that you didn't have a heater, but you had a stirrer on. So you're getting in shaft work, which is a function which your stirrer is putting in. But then maybe you don't fix the volume. Don't fix the volume. But then what do? You actually allow your piston to move up and down, and you insulate it. So that means what? So Q is equal to 0, but then also still you are still using your stirrer now to move your work, your piston. So it's still force over distance. So you can either put in work through a stirrer, or you can put in a work through a piston. So in the PV space, when you add your work up, where your W piston plus your W stirrer, that equals your total work. And as we know that work on the UV space, it is like, it depends on the path, but in your PV space you can add your work, and you can add your stirrer work, and it will add to your work adding into the system. And then also you get a case where you don't insulate, you don't insulate, but you fix the volume. So if you fix the volume and you don't insulate, what's that's going to happen? And you don't, and then so okay, you don't insulate, then you fix the volume. So what happens? So we have state 1 where maybe I put my piston on, or I put my stirrer on, and then I have a change in my pressure and my volume. Okay, and so then I move to another stage where I have my fixed volume, so I lock my piston is locked, and then I let it to rest, and then after some time, so my volume is fixed. So my volume is fixed and my volume is fixed, right? So this is at time equals 1. I did something where I added in work by my piston or my stirrer, and then at time 2 I go, okay, immediately afterwards I am going to fix my volume and leave it to rest. So if I fix my volume, but then after a while maybe I realize my pressure actually decreased. Why? It's because maybe my temperature decreased because of heat transfer. And then that's when you get that your delta U term actually needs work plus Q. And this is when you leave it after some time, like T infinity, or T2 plus 10 T2 plus a certain amount of time. Okay, so basically what this is to do is to show you that the delta U plus WQ is your first law of thermodynamics, but more than that, it also gets incorporated into your energy balance. So we recapped on internal energy, that is extensive, and yeah, you can sum up the work done by the piston and the stirrer for each path in the PV space. And then therefore what happened is we this is, so you could work this out mathematically, and then when you compare it for it experimentally, you can actually find that there might be inefficiencies in your system. The values aren't your true values of your mathematics. So then ask yourself, why is that? But then I just want to take you to the postulates, and the postulates is basically where there are 3 things I need you to know from the postulates. It's when we're introducing a rigid container. So you have a rigid container, adiabatic process, and impermeable. So rigid means your volume is constant, adiabatic, you don't allow heat transfer, and impermeable barrier, you just you don't allow mass transfer to occur. But what I want you to take away from the 4 postulates, there are 4 postulates, that your system can be described by U, V, and N. Okay. More than that, it can also be described by S. It can be described by S, entropy. And because at each equilibrium state you can have internal energy, volume, and number of moles, but you can also have S. And then also that S is greater than 0. Your entropy change with respect to the U total entropy is greater than 0. Your entropy is also extensive, it's also additive, and it's maximum at equilibrium. So knowing all of that, like the 4 postulates, just to walk away, your 4 postulates, your system can be described by U, V, and N. And then your ds tot by your du tot is greater than 0. So your entropy, there exists entropy because we did a case study for when you allow heat to transfer between your barrier when you remove one of the constraints, then that means like your total delta U equals 0, but then and your Q also equals 0, so that doesn't make sense. Therefore, there is this concept called entropy, which helps you understand your system even more. And therefore, so each equilibrium state can be described by entropy, which is greater than 0. And then your entropy is extensive, and it is additive. And the same goes with your other state functions, your enthalpy, your internal energy, your Helmholtz, and your Gibbs. And then for entropy is maximum at equilibrium. And using these postulates, we managed to actually get to a state where, okay, what does that mean? We managed to find out more information about temperature. So that led us to the other slides later on, where we relaxed one of the constraints. So we had a thought experiment where your barrier on the outside and on the inside was impermeable. And then you have U and V and N, and this is side 1, and U, V, and N and side 2. And there it's insulated, so it's insulated, like the overall thing is insulated, and also your barrier, the middle piece is insulated, and there's impermeable. And then also you'll have a rigid. So now, to find what T was, what we actually did is we relaxed one of these. And in the class example, what we do, we said that Q was not 0 for the middle barrier. Yeah, for the middle barrier. For the middle barrier over here. Okay, I'm not going to spell it. But yeah, so we said that T was, that the Q was not 0. So Q is not equal to 0 for the barrier. So it means that we relaxed the Adler-Beer constraint and we allowed heat to transfer. But we couldn't do an enthalpy, we couldn't do an internal energy balance because our total U-tot would have been 0. So then what we did is that we rather figured out what entropy, so we used this equation, T ds plus P dV plus your potential energy dNi. And what we did is we said, okay, fine, let's use this and find it for side 1 and find it for side 2. And then we use postulate 3, knowing that you can also get your total entropy is the side 1 plus side 2. And then more than that, we also said du total, because it's additive, is also equal to 0. Because if we relax the Adler-Beer constraint, if you transfer some energy from U1 to U2, then your total change in entropy is the same, because if you look at the whole box, if you have 100 and then 100 was in state 1, and then you transferred energy to side 2, and then at state 2 then your total energy was still 100. Therefore, even though side 1 and side 2 saw energy transfer, overall your U total, your change in your U2 total there is no change. Okay, so that's why we managed to get that U1 equals U2, and from there we derive this equation. We ds tot by du1 is 1 over T1 minus 1 over T2. And then we introduce, because of postulate 4, is entropy is at its maximum. So therefore at its maximum you get this to be 0, which implies T1 equals T2 at equilibrium, because entropy is its maximum at equilibrium. So that meant that T1 equals T2, and further, and then like before you even reach equilibrium, you still have a driving force. So that kind of tells you, because you could also look at it for side U2, so that kind of tells you that, okay, fine, there's a driving force. And then on this side, like, you have T1 greater than T2, and this side you have T2 greater than T1. And then you know from the relationship that T equals du by ds. But because du by ds, the total derivative of s with respect to u is greater than 0, that also means that T is also greater than 0, and it's positive. So that means that this T behave like our thermodynamic temperature T, so that equals your thermotemperature, because at equilibrium they are equal, thermotemp. And this thermotemp, because it must be greater than 0, is actually thermotemp in Kelvin, so it's your scientific temperature. And it's independent of the amount of material. But also where T1 equals T2 at equilibrium, this is actually the zeroth law of thermodynamics. So therefore we used the postulates, and we used what we know about du equals T ds minus P dv to help us find out more information about U by relaxing one of the constraints on our little box, which was impermeable, rigid, and insulated. So we relaxed one of those, and you can further derive more, you can like find out more relations by trying to do relaxing the other constraints. But the takeaway from this lecture was just the postulates and actually finding out what T is. But now at least we know a bit more that in a system there is also the system that can be described by entropy. So S is entropy. So S equals entropy, yeah. So S is actually entropy, and you know these properties of entropy where it's extensive additive and maximum at equilibrium, and the ds tot by du tot is greater than 0, which like will help you understand entropy a bit more, and to help you understand where temperature fits into the great scheme of the physical variables. Right, so you know the conservation of energy, you know entropy, and the postulates, and the equilibrium temperature. You know it because we derived it, and we proved that we wanted to understand more about temperature, because in thermodynamics we are starting to just want to understand more what you already know in your day-to-day life, and know more about it for equilibrium circumstances, because equilibrium tells us what we know. Like in thermodynamics tells us what we know, and equilibrium states take us to a point where we can go, oh, why is equilibrium so important? Equilibrium is important because it tells you the place where you can best operate. It's eventually where your systems end up.